So today we are going to look at empirical formula and molecular formula. We are going to talk about how they are important in chemistry, and we are going to also look at some of the important calculation involving this concept as well. So to start with, the empirical formula is the simplest whole number ratio of atoms in a compound, while the molecular formula shows the actual number of atoms of each element in a molecule. So let's say for instance we have glucose, that is CH12O6. So you agree with me that there are 6 atoms of carbon in this compound. Then we have 12 atoms of hydrogen and 6 atoms of oxygen in this compound. So those are the actual number of atoms of each element in this particular compound, which is glucose. So that is the molecular formula of glucose. So in simple terms, every molecule of glucose contains this actual number of atoms, which is 6 atoms of carbon, 12 hydrogen, and 6 atoms of oxygen. So that is why it is called the molecular formula. Every single molecule of glucose contains this exact actual number of atoms. On the other hand, the empirical formula is used to show the simplest whole number ratio of atoms in a molecule. So let's say we are given this glucose now. Why we actually need the empirical formula is to compare, like, how many carbon atom are there to hydrogen or oxygen atoms. Are the hydrogen atom more, or are they less than the oxygen or whatever atoms? That is just simply what the empirical formula shows. So if we are given a molecular formula, like let's say glucose, as we can see, and we are asked to deduce the empirical formula, all we need to do is just find a number we can divide each of the subscripts in the molecular formula with, and then we will arrive at the empirical formula. That will give us the simplest whole number ratio of the subscripts in the atom. For instance, if we divide the molecular formula by 6, we are going to have C1H2O1, and that is the empirical formula. So let's say we are given the molecular formula of butane, which is C4H10, and we are asked to deduce the empirical formula. So if you have been following what we have been saying, all you need to do is just find a number we can divide the subscript with that will give us a whole number. And if you are a good student of maths, you will agree with me that if we divide the both subscript with 2, we are actually going to arrive at a whole number. So that means the empirical formula of butane is going to be C2H5. So what if we are given a molecular formula of H2O and we are asked to find the empirical formula? So of course you know that the empirical formula is the simplest formula we can get. That is the simplest whole number ratio. But when you look at H2O, you know you can't divide any of the subscripts further. So that is the simplest whole number ratio you can actually get. So that means the molecular formula will be the same as the empirical formula because it cannot be divided further. As a general rule, whenever the subscript of a molecular formula cannot be further divided, then that molecular formula will be the same as the empirical formula of that molecule. More example of this is seen in carbon dioxide and methane. Let's talk about a scenario whereby we are given an empirical formula, and then we are asked to find out the molecular formula from the empirical formula we are given. Like for instance, let's say we are given CH2O, and then we are asked to find the molecular formula of that empirical formula CH2O. So how do we go about that? So if you are given this particular problem, what you need to do is to first find the empirical formula mass. That is, you do that by finding the mass of each of the molecules in the compound you are given, like in the empirical formula that you are given. For instance, in this formula we have carbon, which have a mass of 12, and hydrogen, which has a mass of 1. When you times it by two of the hydrogens we have, you have 2. Meanwhile, oxygen has a mass of 16. So when we plus all of the molecules in this empirical formula, we are going to have a empirical formula mass of 30. Meanwhile, just so you know, there is no need to actually memorize molecular molecular masses, because they will be provided to you. Like when the question is being asked, they're going to provide you with the masses that you need to calculate, like for the empirical formula. And the next thing that will be provided to you as well is the molecular mass. The molecular mass, we are trying to find the molecular formula, but for us to find the molecular formula, we need the molecular mass of that particular empirical formula, because we do not know the molecular mass, and that is what we are finding. So but for we to find it, we need the molecular mass, but it will be provided as well, like with the question. For this particular empirical formula, the molecular formula mass is equal to 180. Now always have in mind that molecular formula the molecular formula mass will always be equal to the empirical formula mass times the multiplication factor. When we get this multiplication factor, which is n, that is what we are going to use to find the molecular formula. Now the molecular formula mass is equal to 180, while the empirical formula mass is equals to 30. So we will find the multiplication factor, which is n, by dividing 180 by 30. This will give us 6, which means that 6 is the multiplication factor of this empirical formula. So all we need to do is just multiply the empirical formula by 6. So if we are to multiply CH2O by 6, we are going to have C6H12O6, and that is the molecular formula of this empirical formula.